Hello, welcome to lecture number 25 for engineering statics over sections 10.1 through 10.3, where you're going to get introduced to the moment of inertia and the parallel axis theorem. So today we're going to look at what the moment of inertia is and figure out how to calculate it by integration, and then we're going to apply the parallel axis theorem. So the reason that we're looking into moment of inertia is because it is very important in figuring out when materials will tend to deflect or bend. So it matters where the material is on how it's going to withstand some of the stresses that it has. So calculating that information helps tell us how we should shape our beam or whatever we're going to build in order to be able to handle the stresses that it's going to undergo. So let's start our notes. So the area moment of inertia is a geometric property that describes how a shape is distributed about a specific axis, influencing its resistance to bending or deflection. So there's a picture below, and this is just an example to show you that if you have these two planks and you put the same load on them, one plank might tend to bend or bow because the material direction, there's less material in the direction holding it up. So you can see that the plank on the left has more material located further from the actual bending axis, which makes it stiffer. So the higher the moment of inertia, the more resistant it is to bending. So the resistance to bending can be quantified by calculating the area moment of inertia of the cross section. It is denoted using the letter I, capital I, and it has units of length to the fourth power, which is typically meters to the fourth or feet to the fourth. It reflects how the cross section is distributed relative to a particular axis. It is not a unique property of a cross section. It varies depending on which bending axis you're considered. In other words, if you look at the picture below, if I define the bending axis as this horizontal piece, it's different than if I was to make it vertical. Cross sections that locate the majority of the material far from the bending axis have larger moments of inertia, which you can see the moments of inertia are listed above them. So it is more difficult to bend them. So the higher the number, the more difficult it is to deform or bend them. This is one of the reasons the I-beam, which you see above, the one that looks like the shape of an eye, is such a commonly used cross-section for structural applications because most of the material is located far from the bending axis, which makes it very efficient at resisting bending while using a minimal amount of material. All right, so let's figure out how we're going to calculate this. So in this example to the right, you can see a plate that is submerged in liquid. So the pressure of the liquid at a distance y, you can see it's shown over here, it's shown y, below the surface is given by gamma times the distance y. P equals gamma y, where gamma is the specific weight. Of the liquid. The force on the area dA that is shown at that point is dF equals P times dA. And the moment about the x-axis due to this force is y, because that's the moment arm, times dF. And the total moment is if you integrate over the area of y df, which also equals integral over the area of gamma y squared dA, which equals, gamma can be taken out of the equation because it's a constant, y squared dA. That's what we're looking for. So for the differential area shown to the left, so the big thing is coming up if that was confusing. We're going to straighten it out in a minute. So for the differential area shown to the left, this little box, the moment of inertia about the y-axis is equal to x squared, the distance of x squared times the differential area. For the differential moment of inertia about the x-axis, it is equal to y squared times dA. This is kind of using our moment arms. And then I'm going to introduce something new called the polar moment of inertia. And it is equal to the integral a r squared dA. And the moments of inertia for the area are obtained by integration. In other words, we're going to integrate to figure out what I of x actually is, because I of x is the integral of di of x. So it is y squared dA. I of y equals the integral over the area of x squared dA. And the polar moment of inertia about pole O is equal to r squared dA, which is the same as x squared plus y squared dA, which is also the same as I of x plus I of y. The only other little note about this is that the second moment of inertia relates the moment of inertia of an area about an axis passing through the area's centroid to the moment of inertia of the area about a corresponding parallel axis. By including the area of the cross-section A and the distance D between the two axes. This is also called the parallel axis theorem. So what this equation looks like, so if I am using the information up above and I've got this picture to the right, those equations are going through the centroid. If I want it anywhere but the centroid, I need to use this other equation. So I of x equals what it is for the centroid, IC of x, plus the area times the distance in the y direction squared. I of y equals IC, so that's about the centroid of y, plus AD in the x squared. And the polar moment of inertia equals about the c plus and the area times the distance squared. All right, we're almost done. We just have a little bit more. So to determine the moment of inertia, first choose your element, dA. So number one is choose the element dA. Quick note on this, it is really much easier. You have two choices, but it's much easier to select the element that is parallel to the axis you're trying to calculate for. And if y is easily expressed in terms of x, then choosing a vertical strip with a differential element dx may be advantageous. So it's easiest if I am looking for I of y, I'm going to choose a element that is parallel to the axis, like you can just see to my right. Whereas below, it's parallel to the x-axis, so I would want to be using my about the x. So next you're going to integrate to find the moment of inertia. Note that if the differential element is d of x, y needs to be expressed in terms of x. And the integral limit must also be in terms of x. The opposite is also true. If the differential element is d of y, x and the integral limit need to be expressed in terms of y. So let's look at some examples to try to help you picture what that looks like. So example number 1, it's asking me to determine the moment of inertia about the x prime and the y prime axis of the shaded area shown. Now notice that the x prime and the y prime are through the centroid. So I don't need to use the parallel axis theorem. So I am only going to use what we directly found before. So we are looking for what I of x prime equals. So I've got a strip already determined. I'm going to use this gray strip because I'm looking for it for the x-axis, so I want to choose a strip parallel to the x-axis. So the area of my strip is equal to dA, and that is equal to 2 times b over 2. So it's basically b, that's the length of the base, times dy prime, little apostrophe, which is the same as b times dy prime. So that's my area. So I know that my di of x prime equals y prime squared times dA, which I just solved for dA. So it's going to be y prime squared times b dy prime. So to actually find I of x prime, I need to take the integral of that over the area. I need to take y prime squared dA, which I already found is the integral. And I'm going to take the integral, so I'm looking at dy prime is my part, so I'm going to look to take the integral about what is on the y axis, the y area. So I'm going to go from negative h over 2, because I'm looking at my x prime being my axis, and I'm using dy prime. So I'm looking at the y side. So I've got negative h over 2 to h over 2 is what I'm varying in my y direction of y prime squared times b dy prime. So basically, if I keep going, b is a constant, so I can pull it out. And then I just need to integrate y prime squared, which is going to give me, y prime to the third over 3. Integrate that from negative h over 2 to positive h over 2, which is going to give me b times h over 2 cubed over 3 minus negative h over 2 cubed over 3, which, if I keep working that out, I get equals b times h cubed over 24 And this negative is going to come out to be a positive h cubed over 24, which is going to tell me that I about x prime, my moment of inertia about x prime, is equal to bh cubed over 12. And that is, in fact, moment of inertia for a rectangle about the x-axis, if you look at the table that you've got. Now we need to do I of y prime. Excuse me. I of y prime equals question mark. So now our area, I'm going to switch because I need to do an area that is parallel to the y-axis. So I'm going to use my little blue, my blue rectangle this time that's got d of x. And so I'm going to say that my area is equal to 2 times h over 2, or h, times d of x prime, which is going to be equal to h times d of x prime. And remember, h is a constant, so in the integration I can pull it out. It's not part of the variable. So my equation for diy is equal to x squared times dA, which equals x prime squared times h dx prime. So when I take the integral, I'm going to do iy prime equals the integral over the area of x prime squared dA. Which, remember, I'm using the x this time, so I need to use my information for my limits to be the x direction now. So I'm going to have from negative b over 2 to positive b over 2. It's going to be my limits times x prime squared times h dx prime, which I can pull the h out, which equals h, and I'm going to have my integral from negative b over 2 to b over 2 of x prime squared dx prime, which is going to be h times x prime cubed over 3 from negative b over 2 to positive b over 2, which means it's going to be h times b over 2 cubed over 3 minus negative b over 2 cubed over 3, which is going to end up giving me h times b cubed over 24 plus b cubed over 24. So it looks a lot like I of x, it's just our variable, our numbers are swapped around. So I'm going to get that I y prime equals h b cubed over 12. Which again you can find in your tables. So let's look at this rectangle again, but this time I want to find the moment of inertia for the area passing through the base of the rectangle. So I want to find it through this xb. I want to find I of xb. So I'm going to have to use the parallel axis theorem, which the parallel axis theorem says if I want to find Ix of b, it is going to equal what I found before, I of x prime, plus the area times the distance squared. So I already calculated that I of x prime before equals bh cubed over 12. Now I'm going to look at the area of the element is the base times the height, bh, and the distance to this axis, this distance is what it's looking for, the y distance, and that is going to be distance equals h over 2. So our distance equals h over 2. So to find Ix of b is going to equal 1/12 bh cubed plus bh times h over 2 squared, which equals 1/12 bh cubed plus 1/4 bh cubed, which equals 1/3 bh cubed, which equals Ixb. So it's just a little bit different because we had to add a little bit for the distance and use the parallel axis theorem. All right, so let's try another example. So I've got this in two different ways. I'm going to do this using a horizontal strip for this example. But if you want to see what it would look like using the parallel axis and a vertical strip, you can look in my notes. I included my notes in Schoology. But I told you it's easiest to use the parallel, what's parallel to the axis you're trying to find. So I'm going to use this horizontal block for this example. So I'm going to use dy, which means that I'm going to need x in terms of y. So right now I have the curve is y squared equals 400x, but I need to have x defined in terms of y, which is going to mean that y squared over 400 is equal to x, because I know I'm going to have to plug that in at some point. So notice that the area, notice this is the length of the rectangle I'm talking about, because we have it's 100 millimeters. We defined x as the distance from the axis to this point. So 100 minus x is the length of my rectangle. So my area dA equals 100 minus x, because that's the length, times the height, which is dy. We can rewrite that to be dA. I'm going to substitute in what I know, because I'm using dy, I'm going to want x in terms of y. I'm going to substitute in the 100, I'm going to substitute in for x, that x is y squared over 400 dy. So I know I'm going to need to have it in terms of y. All right, so let's find our I about the x-axis. I of x is going to be equal to a y squared times dA. Now our limits are going to be what's on the y-axis. So we're going to have from 0 to 200 millimeters. It's going to be the limits of our integration. And then we're going to have y squared times dA, which is 100 minus y squared over 400 times dy. I can rewrite that to be the integral from 0 to 200 millimeters of 100 y squared minus y to the 4th over 400 dy. And if I integrate that, I'm going to get that that equals 100y squared is going to be 100y cubed over 3 minus y to the 5th over 2,000, because 400 times 5 is 2,000, and I need to plug in my limits, 0 to 200 millimeters. And if I plug that in, I'm going to have 100 times 200 cubed over 3 minus 200 to the 5th over 2,000. And I get a really big number, but I'm going to use my scientific notation. It is 1.067 times 10 to the 8th. We're going to use scientific notation for a lot of what we do with the moment of inertia. Remember, my units are to the 4th. All right, that's your answer. It's much more challenging to do a vertical strip, but if you're curious and want to see how it works, you can look in my notes. I think I've got one more example that I'm going to do. So I'm going to skip over the vertical strip. And we are going to first do example number 3, determine the moment of inertia about the x-axis. So while I'm doing it about the x-axis, I am going to use a horizontal strip because I want it to be parallel to the x-axis, which means that my differential element is dy. I have defined already that my x and y at this location are as shown. This is my x, that means this is my x, and that this distance is 1 meter minus x, so 1 minus x. So now if I'm looking at this for area, the area of the rectangle, of my rectangle shown is dA equals 1 minus x times dy, which I'm going to have to find x in terms of y then. So for my curve, I've got y cubed equals x squared. That's what they gave us. So if I turn that in terms of x in terms of y, I'm going to have y to the 3/2 equals x. So now I need to find my about the x-axis equals over our area, y squared dA is going to be our formula. We are going to integrate. Our integration limits are on the y-axis, which in this case is just 0 to 1. So I'm going to integrate from 0 to 1 of y squared times dA, which is 1 minus x times dy. And if I plug in what I've got for x in terms of y, that's going to be from 0 to 1 meter, y squared times 1 minus y to the 3/2 dy. So I'm going to distribute that y out a little bit to make it a little bit easier for me to integrate. So I'm going to have 0 from 0 to 1 meters. I'm going to have y squared minus y to the 7/2, because I've got 2 plus 3/2 gives me 7/2 dy. And I can integrate those pretty easily to where I'm going to end up with this equals y cubed over 3 minus y to the 9/2 over 9/2 from 0 to 1, which ends up equaling 1/3 minus 1 over 9/2, which equals 1/3 minus 2/9, or 1/9, which if I do that on the calculator is 0.111 meters to the 4th. That is I of x. I could have gotten that same information by using a vertical strip and the parallel axis theorem. It would have just been a little more complicated. So now we've done I of x, so let's do the same thing for I of y. So now if I'm doing I of y, I'm going to choose a rectangle that is parallel to the y-axis. So my differential element this time is d of x. And so the area of my rectangle is equal to y dA equals y times dx. And our curve that we're given says y cubed equals x squared. This time I need y in terms of x because I'm using a differential element of dx. In other words, that's going to mean that y equals x to the 2/3. So now if I do my moment of inertia about the y-axis, I'm going to have over our area x squared times dA. Now I'm integrating over x, so my limits are going to be from 0 to 1 meter, because that's what my x limits are. I'm going to have x squared times dA, which is y times dx, which I can plug in what y is, 0 to 1 meter, x squared times x to the 2/3 dx, which equals 0 to 1 meter. X squared times x to the 2/3 is going to be 8/3, x to the 8/3, because 2 plus 2/3 gives you 8/3 dx. If I continue to integrate, I'm going to get that x to the 11/3 over 11/3 from 0 to 1 meter, which equals 3 over 11, which equals 0.2727 meters to the 4th. Is our I of y. You can also do this with a horizontal strip. It just have to use the parallel axis theorem, and it's a little bit more work, but you can look that up if you're interested.